Vision transformers have emerged as powerful models in computer vision, particularly for image classification tasks. In this project, we implement a ViT model for image classification on the CIFAR 100 dataset. Then we explore ViT's applicability in data-driven forecasting of physical system dynamics. The motivation for this exploration arises from the need for efficient and accurate forecasting models in physical systems, especially those governed by complex dynamics such as fluid flow or mechanical deformations. For image classification, the first class in the vision transformer model is the patch embedding class. It splits up each image in the dataset into smaller patches since it does not use a traditional convolution neural network filter. The convolution layer is used to extract patches from the image. Then the output of the convolution is altered to make each patch a vector. The transformer encoder layer class incorporates multi-head attention where each patch attends to every other patch, improving the model's ability to capture different relationships. Then a feed-forward network is applied to each patch with a GLU activation function and dropout for regularization. Layer normalization is applied to stabilize and speed up training, and the residual connection helps with training deeper networks. Finally, the vision transformer class combines these and outputs the classification for each image. It starts by embedding the input image into patches using the patch embedder. Positional encoding is added to give the model information about the position of each patch. After passing through all the transformer encoder layers, the model averages all the representations to create a vector representing the image. Lastly, this is passed through a fully connected layer to predict the class of the image. In the training loop, the model is set to training mode and the forward pass and loss are computed before backpropagation is performed to update the model's weights via the optimizer. The evaluation loop computes the loss and accuracy of the model on the test set. After experimenting with multiple values for the parameters when training our model, we decide to use smaller dimensions to reduce the computational complexity and got an accuracy of 42%. As we increased the number of epochs, we observed overfitting was occurring, so we used image augmentation to increase the size and got an accuracy of around 48%.
So after we have explored with the re-implementation of vision transformers with the original classification task, we further extended our exploration into performing a forecasting task on the stream mesh datasets, which it has an input dimension of 10 times 10 pixels with XY position and timestamps. And so the first is a data loader that we load the dataset of the .mpz trajectory files of stream mesh simulation that slices the trajectories into input-output pairs using a sliding window of the past states, which is the windows, and we set it to 3, and to predict the future stage, which is the horizon, which is also 3. So we can take in multiple past steps and predict multiple future steps. And onto the patch embedder, which is also pretty similar to the ViT's original patch embedding for images, is that it uses convolutional layers that divide the mesh into non-overlapping patches and projects them into the embedding vectors. And the next one is the transformer encoder layer that applies the multi-head self-attention followed by a feed-forward network with layer normalization and residual connections to stabilize the training. So the key differences between the two models lies between their input and output, which for the classification, the model takes a single image and output class logics to a classification head. And for the forecasting, the model processes a sequence of past frames and outputs future mesh grids via a regression head. So structurally, they are nearly identical except the final head and how the input data is formatted. And for the vision transformer, the complete model for forecasting is that it uses 4 encoder layers and a regression head. The final output is reshaped into the forecasted mesh grids over 3 time steps, each with 2 channels for X and Y positions. And for the training loop, we first have loaded the data from the directories, and we the final ones we used is that we had during the training, each patch is passed through the model to predict the future mesh states. The mean square error between predicted and true states is minimized, and the evaluation was performed both on the in distribution, which is over here, of the eval loader, and also the out of distribution, the OOD loader data. And we also have experimented with different learning rates and found that best results achieved at 1 to the -4th power, and which balancing the stability and generalization. So in the end, with training 30 epochs, we're able to achieve the best train loss and val loss of this, and the final eval loss of 0.0051 and final OOD loss of 0.0174. And we can see this is the graph we have, the visualization we have for the stream mesh forecasting with one-step channel 0. And comparing the ground truth and the prediction, we can see that they're very, very similar. And even looking at the absolute error heat map, the darker colors showing less error, we can see that this image is pretty dark, which is the error is very low. So overall, in conclusion, we see that ViT can be adapted for forecasting physical dynamics, and with just architectural adjustments, it generates beyond classification. And some of the potential future work we could consider is to integrate the Koopman operators for better dynamic modeling as in the original plan. Thank you.